Hello, my name is Tony, and I'm here to present our work on latent denoising diffusion probabilistic models. Traditional diffusion models operating in pixel space are extremely computationally expensive, requiring thousands of inference steps. Generating just one image could take several minutes on even powerful GPUs. Our goal is to maintain the high quality that diffusion models are known for, while improving their efficiency. Our approach involved re-implementing several state-of-the-art techniques. We started with DDPM as our foundation, implementing DDIM for faster sampling, utilized latent diffusion to reduce computational overhead, and incorporated classifier-free guidance for improved conditional generation. We work with the ImageNet 100 datasets and apply standard normalizations and random horizontal flippings as augmentations. The diagram here shows our overall architecture. We encode original images using a lower dimensional latent space using a VAE. The diffusion process happens in this compressed space. We inject conditional information through classifier-free guidance and finally decode back to pixel space to get our generated images. Key components include our UNet with attention mechanisms, positional encodings for time steps, and VAE for efficient compression. Our project started with a basic DDPM implementation using a UNet architecture. The forward process gradually adds noise to the picture according to this equation here, transforming clean images into pure noise. The model then learns to reverse this process by predicting noise at each step, minimizing the difference between the predicted and actual noise during training. One key optimization was implementing DDIM, which offers a deterministic alternative to DDPM. Instead of requiring hundreds of Markovian process steps, DDIM used a deterministic update route allowing for much larger steps. This reduced inference time dramatically. We presume that you will generate high-quality images in just 50 steps instead of 1,000, achieving a 20x speedup while maintaining quality. By compressing image space using a VAE, we reduce dimensionality significantly while preserving essential semantic information. For conditional generation, our CFG eliminates the need for a separate classifier network. By interpolating between conditional and unconditional predictions, we will achieve better control over the generation process. So here's the set of preliminary results we got from the midterm training using just a DDPM scheduler with a subset of data. You'll notice that even some images are generated, the contents is highly unrecognizable and frankly quite disturbing. So you'll notice that the DDPM scheduler to finish 10 epochs will take 1.5K steps. Under the same settings, if we switch to DDIM, you'll notice that 10 epochs only take 29 steps on the same subset of data, so which reduce the inference times dramatically. We can further improve on this by incorporating a VAE that converts image into latent space. And on the AWS platform using A10G GPU, we're able to reduce the training time per epoch by a third. So this is the training result that we got using a DDIM scheduler with VAE and CFG. So up until the recording of this video, we're still in the middle of training because the training time takes very long on the full dataset. And here's the results that we got from less than 30 epochs. And you will notice that the image quality is still subpar, and we do sincerely apologize for this. However, there are some recognizable content that are generated. You'll notice that in the fourth picture, there's some creatures that looks like a duck. Using the results that we have so far, we only achieve a FID score of 275 and exception scores of 1.89. Regardless, for future directions, we still plan to explore other types of VAE for improvements, such as VQ-VAE, which learns a discrete latent space rather than a continuous one. We will also experiment with different architectures of the UNet models and explore options like diffusion models with a transformer, which achieves the state-of-the-art FID of 2.27 on the ImageNet benchmarks. Last but not least, we still believe that the DDIM's deterministic formulation allows for larger step size without quality loss. Latent space operation reduce computational overhead, and CFG provides better control. These improvements reduce computational requirements, enable better user-gated generations, and open up practical applications in content generation, design use, and data augmentation scenarios. Thank you.